Sampling design. Elements of sampling designs. Our choice of sampling design is driven by management objectives and sampling objectives. Primarily, why are we measuring what we're measuring? Sampling design encompasses the practical components of any sampling endeavor. What do we want to measure? How is it going to be measured? And where are we going to measure it? We can see from these two statements, one is a statement of management objective, and the other is a sampling objective for the same, related to the same design, that they incorporate very different concepts. A management objective focuses on stating very specific criteria about a desired condition or a desired state or change for a population. The population is well defined, as is the attribute that is being measured. And this is related to an overall management goal. A sampling objective, on the other hand, is specific to the sampling endeavor, and it reflects the level of confidence that we want in our estimate, as well as a statement about the desired level of precision needed in that estimate. Both of these statements are important to consider in the selection and determination of sampling design. There are numerous elements in sampling designs, and these include the identity of the population or area of interest that has to be very clearly stated, the attribute or attributes to be measured, the method that we're going to use to measure the attribute, the type of sampling unit, as well as the dimensions of the sampling unit. We need to determine how units are going to be positioned in the area of interest, as well as the number of sampling units. This refers to sample size and is often referred to as, it's represented by the letter N. Finally, the subsampling intensity, or the number of observations taken within each sampling unit, need to be considered. Now first, where do we sample? We have to clearly identify the population or area of interest, and these can vary based on scope and scale. We could decide that we're interested in making inferences about a relatively large area, a region, or a state. We could be interested in focusing on a particular vegetation type, one that is associated with a management unit, or in some cases we delineate specific areas, such as key areas or critical areas within the management unit, and would focus on those. Sometimes the scale is simply wanting to focus on the vegetation in a particular ecological site. What we sample includes the attribute that we plan to measure. So an attribute is a particular variable that can be measured on vegetation. And there are multiple methods that are available to measure each of the important plant attributes. The selection of the method is very case specific and is influenced by our management and our sampling objectives. It's also influenced by the amount of cost and time that's involved, as well as the amount of skill of the observer and the amount of training that is required for an observer to develop those skills. We can see here in this table for these various plant attributes that each can be measured with a variety of different methods. And we will be discussing these plant attributes as well as measurement methods in more detail in subsequent lessons. Sampling units come in a variety of types, including points, transects, quadrats, or plots, individual plants can be considered a sampling unit type, as well as plant parts such as fruits or tillers or stems. And we also can have combination sampling units. For example, in the lower right, we see an image with two women who are measuring cover. They are using a combination transect and quadrat sampling unit. So here's a transect. They position a quadrat at one location on the transect, take their measurements. They will then move this quadrat to another position on the transect and take multiple measurements along the transect. So that's an example of a combination sampling unit. Our choice of sampling unit depends first on the attribute that we have selected. Certain attributes, such as production, can only be measured in quadrats. Cover, on the other hand, can be measured with either points, lines, or quadrats. And so the choice of whether we would use points, lines, or quadrats depends on other aspects of our objectives for cover. The sampling objectives, including desired precision, confidence level, etc., are important, as well as vegetation characteristics. This includes the spatial arrangement of plants in the environment, the type of vegetation, whether plants are evenly distributed or clumped into plant patches, the average plant size, and variation in plant sizes all influence our choice of sample unit type. When we're talking about sampling units, we need to consider dimensions, and this usually encompasses the length of transects or the size and shape of quadrats. In general, as we move from a homogeneous into a more heterogeneous environment, we find that in order to improve precision, we need to lengthen transects, and we also tend to change the shape of our quadrats from square to more rectangular. So let's look at a little more detail at an example of the influence of transect length. In this example, we're looking at three schematic diagrams of different vegetation types. First, we see on the left, a fairly evenly distributed homogeneous grassland. In the middle, we have a patchy grassland that has some open space with scattered shrubs. And to the right, we have a woodland with fewer, larger individual trees and some scattered plants. So what happens when we put short transects into these environments? We can see that in the homogeneous grassland, a shorter transect does a pretty good job of encompassing all forms of, or all of the variation in the grassland. And so within an individual transect, it's going to incorporate some areas where there's fewer plants and more plants, and we're going to have better precision or among the transects. The measurements of the transects are going to be relatively close to each other compared to in the patchy grassland with scattered shrubs. In this case, some of the transects, just because they're short, may only be found in areas where there are relatively little vegetation, and some are going to be completely contained in areas where there's high amounts of vegetation. So we're not going to have as good precision in this environment. And the same can be said for the woodland. The shorter transects are not going to produce a very precise estimate. As we lengthen the transect, we can see that in the grassland, for example, the longer transects start to incorporate the variability of the environment. So we have both regions of low vegetation and higher vegetation cover or density in these transects. And in the woodland, in order to get the best precision or greater amounts of precision, we would need to use longer transects still. So let's look at the influence of changing the size of quadrats. And in this case, we're going to be looking at square quadrats in another hypothetical population. In this case, these are plants that are found in dense clumps. With the smaller quadrats, we can see that we have some quadrats that have no plants and other quadrats that are quite full. So there's going to be less precision because there's greater differences in the kind of measurements that we would get among these different quadrats. If we increase the size of the quadrats without changing their location, we start to find that we increase the precision because each quadrat is going to incorporate more of the variability that we see in the environment. So by the time we get to the larger quadrat, we start to incorporate areas that have low vegetation and high vegetation, and this would result in greater precision. Let's discuss the impact of shape. Quadrats can be circular, square, or rectangular. The main effect of these differences in shape is that they have a different perimeter to area ratio. Essentially, there's more edge in a rectangle and in a square than there is in a circle. Now, our decisions about what shape quadrat to use depend on the attribute of interest. It also depends on vegetation characteristics as well as the potential for edge effect. There's a trade-off that needs to be considered between the increased precision that we can get versus the potential of bias due to edge effect. And we'll see that better demonstrated in this slide. Here, we're looking at the effect of lengthening or changing the shape of our square quadrat to more rectangular quadrats. So here with the square quadrat, we've got some quadrats with relatively low amounts of vegetation and some with relatively high vegetation amounts. By changing these quadrats to rectangles, we start to incorporate some of the environmental variability into our values that we would be measuring. And if we lengthen them still into longer, thinner rectangles, we start to incorporate even more of the environmental variability. Remember, the definition of precision is the closeness of repeated measures to each other. And so with this type of a very long rectangular quadrat, we would have the best precision of these three scenarios. The caveat is that there are decisions that need to be made anywhere you have an edge. And when you have those kinds of decisions, there's a potential for bias, where someone may choose to count a plant as in the quadrat or outside of the quadrat in the case of density. And so there's a trade-off between increased precision and the increased potential for bias that needs to be considered when you are making decisions about shape. How we position sampling units is another important characteristic of sample designs. Sampling units can be located in a landscape using a random design, stratified random, systematic, selective, and other types of sampling designs or schemes. This information will be covered more closely in a subsequent lesson. The orientation of transects in the environment is one important aspect that we will discuss now, and this is specific to the orientation of transects relative to a gradient that may exist in the vegetation population. So here we see a schematic diagram of a population, and we can see that there's a gradient from low vegetation cover to high vegetation cover or density. There's just less abundance of plants on the right side of this schematic diagram than on the left side. Now, if we were to position our transects so that they are oriented perpendicular to the gradient or against the gradient, the direction of the gradient, what we will see is that some of these transects will fall only in the area of high vegetation abundance, and some will tend to fall only in the areas with low vegetation abundance. This tends to lead to lower precision because these measurements will be different for each one of the sampling units. On the other hand, if we orient our transects so they are in the same direction or parallel to the gradient, we tend to see an increase in precision, and that's because each one of the transects is going to pick up information from that incorporates the variability of the entire area. So this particular transect here incorporates regions of low and high vegetation density. So we see an increase in precision. Subsampling intensity, or the number of observations that are measured within each sampling unit, affects precision because this influences the amount of information that is gathered per sampling unit. Here we see first an example of a schematic vegetation diagram with 3 transects, and we're measuring cover at 5 points along these transects. If we increase the number of points, we increase the amount of information taken per transect. And we can see that by doing that, we decrease the size of the standard deviation and the standard error. These are our estimates of variability, and a low standard deviation and a low standard error reflect high amounts of precision. Now, one of the caveats of having something to consider when you have relatively or different numbers of subsamples in a sampling unit is the range of possible values that each of your sampling units, in this case each of your transects, can assume. If you have 5 points per transect, there's a fewer range of possible values that can be assumed. You could measure either 0, 20, 40, 60, 80, or 100% cover. Compare that to the range of possible values that can be measured if you increase that to 10 points per transect. So these are things to consider when making decisions about subsampling intensity. Sample size, again, is the number of sampling units that we take or we measure in order to make our estimate of the attribute. And the number of sampling units has a profound effect on precision. In this example, we see 3 transects in a schematic diagram, and then compare that to 6 transects and compare to 9 transects. In all cases, each one of these transects is estimating cover using 5 points, so we're holding the subsampling intensity constant. And we can see that by increasing the number of transects, we have a decrease in the standard deviation and the standard error, and this translates to better precision. So why does sample size affect precision? First, when we increase the sample size, we reduce the influence of outliers or unusually high and low observations. For example, if we were rolling dice and we rolled the dice 3 times, just by chance, we could get a very low observation and a very high observation, and then the mid-range observation of 7. This sample has a mean of 7, which you would expect for dice, but it has a very high standard deviation. If we increase the number of rolls, or the sample size, we still have the low observation of 2 and the high observation of 12, but by adding additional observations, we reduce the variability, we reduce the influence of those outliers, which results in a lower standard deviation. In addition, increasing sample size tends to reduce the standard error, and this is simply due to the mathematical formula that we use for standard error. Standard error is defined as the standard deviation divided by the square root of n, or the square root of the sample size. If we divide by a smaller number, it's going to be bigger than if we divide by the square root with a larger sample size. It's simply due to differences in math. So if we hold the standard deviation the same with a larger sample size, or a larger n, the standard deviation is the standard error is automatically going to be lower, simply because of that higher sample size. As a general rule, we tend to increase the sample size when the inherent variability of the vegetation is high. Now, how do we determine what is the appropriate sample size? This is a question that is asked many times when people are trying to determine their sampling design. The sample size that we choose is influenced by our sampling objectives. What is the desired confidence level, and what is the desired precision that we want for our estimate? So, for example, if we state that we want to be 90% confident that our estimate of density is within plus or minus 20% of the estimated true mean density, that is going to drive or greatly influence the required sample size. Required sample size is also influenced by the inherent variability of the population. When we are sampling in an area that is relatively homogeneous, in general, we don't need as many samples in order to get a precise estimate. Compare that to areas that are more patchy or highly variable. You're going to need a larger sample size in order to get a precise estimate. Usually the way we determine sample size is we conduct some pilot sampling in order to determine an estimate of the inherent variability of the population. And we then use sample size formulas to estimate the necessary or the required sample size. There's a variety of different sample size formulas that are available, but they all have common elements. They all include a component that reflects the desired confidence level, the desired range of the estimate around the mean, and the observed variability. So in this case, t-square represents the confidence level that was set, s-squared represents the precision that was observed in the estimate from the pilot sample, and e-squared represents or reflects the desired precision that is set by our sampling objectives. Now, sometimes once we calculate the desired sample size, it's just going to be too large or impractical for us to be able to collect. And in that case, we have to make some sort of adjustment. First, we could change the sampling design components in order to reduce variability. And so in that case, we would consider all of the components that we've considered so far in this lesson. We would consider possibly changing the sample unit type. or the dimensions, the length of the transect, or the size of the quadrat, or the shape of the quadrat, or how it's oriented in the landscape. There are a number of components that we can change, and with the main objective of reducing the S squared value, or the precision of the observed precision. We could also decide that we don't need to be as confident in our estimate. We could reduce the confidence level, for example, from 90% to 80%, and that would essentially reduce the value of the t-squared component of this equation, and that would reduce the required sample size n. Finally, if we decide that we could increase the acceptable range around the mean. For example, instead of being within 20% of the mean estimate, that if we expanded that to be 30%, that would change the e-squared value. It would increase the e-squared value, and that would also decrease the size of n, or the sample size required. So in conclusion, sampling design is driven by management and sampling objectives. It incorporates numerous elements that can be determined by the investigator, and it's important to carefully select design elements, because we're usually balancing a trade-off between the need for precision and confidence with the practical considerations of time and cost required for sampling.